describing motion without the use of forces. And we have these equations we come up with because there's certain relationships we know. And then we can manipulate those equations that we know, build on them, so that we can actually describe the motion of an object. And what do I mean by describing the motion of the object? I mean we know the initial and final position. Actually, what we really care about is the change. The initial and final velocity, the acceleration, and how long it was moving, the time. And these 5 things, I know it looks like 6, but because what's really important is the change in position. We don't really care where it started and where it ended, because again, choice of origin is somewhat arbitrary. Where you call, maybe when I'm dropping this eraser to the desk, I call the desk 0 height. Well, maybe you call the floor 0 height. Okay, so we've got different initial and start and ending positions for the eraser. But both of us have the same delta y, right? Because it moved the same distance in both of our coordinate systems. So that's really the value that's important here. So those 5 parameters that describe the motion in our kinematics. So we need equations that we can use. If we know a few of these with our kinematics equations, we can then solve for the other ones. That's the key here. And it takes a little bit of calculus to derive these, so I'm just going to give them to you. But they're listed in the book. And we've got our final velocity is equal to the initial velocity plus acceleration times time. We've got an average velocity is just equal to v initial plus v final over 2. Final position is initial position plus 1/2 v initial plus v final times time. That's the average velocity times time. This one we use a lot. Final position is initial position plus initial velocity times time plus 1/2 acceleration times t squared. And then there's one more. V final squared is v initial squared plus 2a times the change in position. Okay, so we have a number of these equations, and then we can use those to solve for our missing parameters, and then we would have a complete, once we know these 5 parameters, we'd have a complete picture of the motion. So let me do a quick example. Let's say we are dropping something off from the top of a cliff, and we have a little object here, and we just drop it. We just release it. And it's some height, 50 meters above the bottom of the cliff. And so we want to know, we want a complete description of the motion. And that's all that's given. Oh, well, there's one other thing that's given. What is that? The acceleration is due to gravity. Okay, and we're going to ignore air resistance. The way I like to do it, because there are these 5 parameters that are so important, right? So I just like to make a quick table of those 5 parameters. So I've got, would you like me to use y's instead of x's here since it's going up and down, or can I just use x? It's moving in one dimension, right? So I'm using x. You could use y if you want when it moves up and down, and x when it moves horizontally. I'm just going to use x here, if that's okay. So I've got some initial position, some final position. Then I've got an initial velocity, a final velocity, acceleration, and time. Those are the key things that I need to fill in. And so first thing I can do, this helps me organize my thoughts, right, when I make this little chart, because the first thing I can do is go fill in what I know. Before I can fill in what I know, I have to do 2 things. So step 1 in solving these problems is to define your origin. You need to know where the origin is. And you can pick it wherever you want it to be. But there are 2 places that make the most sense. What are those? The initial position and the final position. Yes, those make the most sense. I could make my origin way up in the air somewhere. I could make it in the middle of the cliff. I could make it down underneath the ground. It doesn't matter. But the 2 places that make the most sense are either where it's starting or where it's ending. So number 1, define origin. Where would you like it to be? Most students like the lowest point in the problem to be 0 and up to be positive, so I'm going to do that. Okay? So I'm going to make my origin down here. So there's my origin at the ground level. And as I said, most students like up as positive. I'll make up positive, because that's the second step, is define the positive direction, or directions when we have 2-dimensional problems. So define the origin and define the positive direction. So we've done that. Now what I do is fill in this chart. If the ground is 0 and we're starting at the top of the cliff, where's our initial position? 50 meters. And I'm going to write plus 50 meters just to drive home the point, because it could be negative. This is not, I know you're thinking, you're thinking distance maybe can't be negative, right? That something moved. But this isn't distance, this is position, like position on a number line. And if we chose our number line a little differently, like if I chose the ground to be 0 and down to be positive, then it would be on the negative side of the number line if it was above the ground, right? It would be negative 50. So you have to be careful with signs. That's the key to doing these problems. These problems are fairly simple once you get the hang of it. You just have to be careful with your signs and you'll be okay. So I'm just writing plus 50 just so you know that you could have a negative number in here for position. And what's our final position? 0. And what's our initial speed? Velocity? Velocity. We're doing velocity right now. 0 because it's released from rest. Right? So one of the things you have to learn when you're in physics is how to read a physics problem. Little clues like released from rest, free fall, usually means that, right, that's only under the influence of gravity. Smooth surface, later on you'll see slides on a smooth surface. That means there's no friction. You have to learn how to pick up those clues. And the other, I should tell you, wait, before we do this, these kinematics equations only work when the acceleration is constant. So that's kind of a clue also. When you're solving a problem and they say a car moves under constant acceleration along a road, then a light should go off thinking, oh, I can use kinematics equations here. But there are situations we'll get into later on where we have maybe a spring acting on something. And a spring does not provide constant acceleration. The force varies as the spring stretches. So you cannot use kinematics equations to solve a spring problem. You have to have other techniques to solve that. So that's one clue. When they say constant acceleration, you can think kinematics equations.